All right. Hello and welcome to PChem Crash Course 3. So in the first two PChem Crash courses, we went over quantum mechanics and then contribution to energy of ideal gas molecules. In that case, we used the Schrodinger equation to establish the energy levels for translational, vibrational, and rotational contributions to the energy of an ideal gas atom or molecule. And we left it at the fact that there's all these energy levels, but how do we translate this into an average energy of a sample? In this lecture, we're going to address that by explaining what a partition function is and how it can be used to estimate an average energy of a sample. Okay. Basically what we're going to do here is show how the partition function can be used to estimate the average properties. So basically we're going to start out the lecture as talking about how do we identify what the average is. So to know the average, we need to know, if we want to take the average, we need to know the quantities of the atoms or molecules in the sample. So again, we're going to treat this as we have a box of ideal gas molecules, and what are their average energies. So the first step in taking the average is to identify the number of atoms and molecules, or the energies of the atoms and molecules that are in there. This involves identifying the different energy states that the atoms and molecules adopt, or alternatively, the number of atoms or molecules that adopt specific quantum numbers or energy states. So the ability of the atom or molecule to access a particular energy state depends on the energy of the particular energy state relative the energy, the ground state. So how much higher in energy is this state? As well as the temperature of the system. So the hotter the system is, for example, the faster the atoms in the box will travel, the larger their speeds will be. So this says something about the translational energies. Also, the hotter the energies, the faster these molecules will vibrate. So that says something about their vibrational energies. Also, the hotter the temperature, the more angular momentum the molecules will have. So this says something about their rotational energy. Usually electronic energy, we'd have to make it really hot in order to access excited states, but same concept. The same concept that the hotter the temperature is, the more likely that is. And again, we don't have to impart energy by heat. We could impart it by other means, but typically in a chemical system, in a thermal-chemical system, we are talking about adding energy via heat. Okay, so the probability that an atom or molecule exhibits particular quantum numbers is given by this equation, which is a function of the energy in the quantum, the energy of the particular energy level based on the quantum number. So in this equation, Q is the particular quantum number. I've left it kind of vague because we're going to talk about different contributions to energy. Kb is Boltzmann constant. It's equal to the gas constant R divided by Avogadro's number, so it's kind of a concept we're familiar with. It's just taken on a molecular level rather than on a per mole level. Q is the partition function, which is what we're going to cover in this lecture. I also should have said that, EQ, the energy associated with the quantum number. Okay, so what's this partition function? Essentially, it's a sum of all the possible contributions to the energy. So the particular contribution is this one. This is for a single quantum number. Q is going to take the sum of all of the possible contributions, and basically along with their likelihoods based on the temperature. What this does is ensure that probability P or PQ sums to 1. So if we were to take sum over Q of PQ, it needs to equal 1 because it's a probability. So all states have some likelihood, and all of the likelihoods sums to 1. So we can do this. We know for ideal gas molecules, we established in the last crash course what the energy states are. We have equations for all of those. If we want to calculate the partition function, we just need to sum those. There's two ways to do this. For contributions where the majority of atoms or molecules are expected to be in the ground state, we take the sum. So that's, we are basically going to take a sum over Q of, sum over Q of exponential negative EQ over KBT, or we're going to have to do that. For contributions where many atoms or molecules are in excited states, we can approximate the sum by integrating. So integrating conveys a continuous function. So sum does not convey discrete values. Integrating conveys a continuous function. So basically what we're saying there is if the temperature is hot enough that the sample is accessing a bunch of excited states, then essentially those states have become kind of continuous. So we can kind of illustrate that if we think about energy levels for some system. This is my Q equals 0, and then my Q equals 1, and then my Q equals 2. And then you see how they're kind of getting closer together. As I get up, they start becoming much more close together to some point where it's like I can't even distinguish. So like they're getting closer together as Q increases to some point they are non-distinguishable. So when it gets to this point, when it starts starting getting here, you can approximate the sum using an integral, and that can make it easier because it can be easier to take integrals than it can be to take sums. Okay, so because we're using simple models for our energy levels to obtain our energy levels for our different contributions to energy of our ideal gas molecules, the ways to take these integrals and sums has already been done, so it's been done for us. So I'm going to review what those are. So our four contributions to energy are going to be electronic, vibrational, translational, and rotational. Electronic partition function, we're just basically going to assume here that most atoms or molecules are in their ground state. So there is really not much to the partition function. We just have one entry, and that's going to be the ground state. What we're saying there is that the probability, we're going to approximate the probability of the ground state as being equal to 1. We know that's not exactly true, but it's a fine estimate for an electronic structure due to reasons that we've discussed throughout this crash course. It that's rare to get an atom or molecule in its excited state, and even if you do get it there, it relaxes pretty quickly back to the ground state. So excited states aren't contributing significantly to the energy. Now, this is, of course, there's exceptions to this, but in a normal system, this is going to be the case. So here we're going to say that essentially we only have to worry about the ground state, and that the energy of that system is going to be the ground state energy. In this case, the 0 denotes the ground state. Okay, moving on, the vibrational partition function. We talked in the last crash course that the vibrational partition function, most atoms or molecules will be in their ground state. However, it's not as dramatic as for the electronic energy. There will be some atoms or molecules, there will be, atoms don't have vibrational states. So some molecules will be in excited vibrational states. Atoms don't have vibrational states because they don't have bonds, so there's nothing there's nothing to vibrate. Okay, so in other words, we're not in the region where the energy states that are accessible by the molecule are starting to be continuous. So we gotta stay, or we gotta take the sum. We can't approximate by an integral. So to do that, we can write out our general formula. So we basically want to sum all of the energies. The energy levels are given by this expression. So this was developed, or this was not developed, it was given to you in PChem Crash Course 2. So basically what I do is now I have to take this sum. To do this, first I'm going to factor out a piece. So I'm going to sum over the vibrational quantum numbers, which are these values V. And I said in the last lecture it's kind of confusing because I have these vibrational quantum numbers, which I'm calling V, and then I also have this term here, which is the Greek letter nu, which is the vibrational frequency of the molecule. So those two terms look alike, but they are different. Okay, but anyways, I'm going to sum over V, which is this piece here. So that piece I need to worry about, but I have this other piece in here that's just a constant. So I can move that outside, and this has an error, this should have a 2 here, but basically I'm moving this piece outside of the sum. Okay, and so now I just need to sum this piece. Still doesn't look super fun, but I can do it because someone who's way better at this sort of thing than me recognized that this is a well-known geometric series that has a known form here, and I can just use this. So basically what I'm going to do is say here x is equal to the exponential of negative h nu over kBt, and n is equal to v. So that's how I fit into this formula, which allows me to write my vibrational partition function. I'm going to take my preceding term h nu over 2 kBt, and then I'm going to take this 1 divided by 1 minus exponential of negative h nu over kBt. If I simplify that, I get q vib is equal to exponential of negative h nu over 2 kBt all over 1 minus exponential of h nu over kBt. So that's my partition function. I've taken the sum. This is going to give me all, this is going to sum of all the vibrational states between quantum numbers of 0 and positive infinity. So that's all of the ones that are accessible to my molecule, and whether or not they are able to access those, or the probability of them being able to access those, is going to be determined by the temperature. So the hotter the temperature, the more states that are accessible. Okay, so that's my vibrational partition function. Let's put a box around that. Okay, translational. Super funsies. So we have here the translational partition function. If I want to sum this thing, I'm going to have to do so over all 3 dimensions. So I have, if you recall, I have quantum numbers in all 3 dimensions, which means I have this big triple sum. Looks super fun. But a nice thing about the translational states of atoms or ideal gas atoms and molecules is, again, it's an ideal gas. So I have this ideal gas in this box or in this container, but the ideal gas isn't interacting with anything. It thinks it's all alone in the container, and because of that, there is no difference between the X, Y, and Z directions, at least in the perspective of the gas molecule. You know, it can move in any direction. It's going to experience the same potential. So those 3 dimensions, we can say those dimensions are degenerate. So then one thing we can do is to make an approximation here, which is that instead of having 3 different sums with 3 different quantum numbers, I have just one sum, and I'm going to take that particular, or one quantum number, and I'm going to basically say they're going to be the same in all 3 dimensions, so I'm basically going to take the sum over one quantum number and then cube it. So that's one simplification I can make there. Another simplification I can make is that the quantums, or the energy state, the translational energy states, most atoms and molecules under ordinary temperatures are in excited states, and what that means is that they are in this region of the energy states where the states start to look continuous. So another thing I can do is take an integral instead of, why I keep jumping around like this? I can take an integral instead of taking a sum. So I can write this, I can further approximate the sum here by an integral. That is super helpful because the integral for a function such as this one is well known. I'm integrating here over n, and I have an n squared. When I integrate a function where I'm going to multiply by some constant, everything else in here is a constant because I'm integrating over n. So the integral for that type of function is well known. It's pi divided by 4 times the constant, all taken to the square root, 1/2 power. And so because of that, I can easily integrate the translational partition function. So something that originally looked like a nightmare now looks much easier, and I can easily calculate that. I get this value here. Jumping around some more, I wish that it really would not do that. This has this, and here we have this a cubed piece. If you recall from PChem Crash Course 2, we were writing this function for a particle in a cube. Again, our box might not actually be a cube, but if from the perspective of the atom or molecule is that there's nothing else in that system, it really doesn't matter if it's not cubic, right? To the atom, it doesn't know. So we can approximate it as a cube. The box length the box length cube is going to give us a volume, which is also nice because this is an ideal gas molecule, and so we know things about the volume of those ideal gas molecules. So this is going to give us our translational partition function for our ideal gas, which is going to be 2 pi m, which is the mass of an atom, over h squared. H squared is Planck's constant to 3/2 power. And then we're going to multiply that by the volume of the system. Okay, so that's our translational partition function. Okay, next, our rotational partition function. So most molecules will be in excited rotational states at ordinary temperatures. This means that we can use an integral instead of a sum. I'm not going to go through the steps at all. This is because the rotational partition function is a little bit more complicated due to the fact that it's got this moments of inertia piece that I just don't want to get into the math of having to simplify and deal with. So instead I'll say you can basically perform the same operations as above, and when you do that you arrive here at the rotational partition function. Again, this is for a diatomic heteronuclear molecule, but you kind of get the idea. We're not, in this class in kinetics, we're going to deal mainly with translational partition functions, so I'm not going to get into the details of the rotational one. But anyways, this is how we get these various pieces. So we have our translational, our rotational, our vibrational, and then we also said that for our, actually let me do it this way, our electronic, we're just going to say it's approximately equal to 1 and not really deal with it. These are all fine assumptions at the level that we're going to use them in the next lecture when we finally bring this back to kinetics of processes involving ideal gases. Okay, so why are these necessary? So we want to remember what we're trying to do, which is to get back and calculate the average energies of a sample. So, and since we can't know the quantum numbers, what's a model to do this? Okay, what we're going to do is we're going to sum up, we're going to create the partition function, which is going to tell me essentially all of the possible contributions to these various energies depending on the temperature. So if the temperature is low, we're only going to get a couple of these energy states that are really contributing to that value. If the energy is higher, if the temperature is higher, we'll get more of those energies contributing. Okay, but that that gives me what's possible. It doesn't tell me what's available in the sample. So, and again, that's something I can't know because I can't measure it. But what I can do is use Boltzmann statistics to estimate the average values based on equations from statistical mechanics. So I'm not going to get into the derivation of those. It requires a lot of discussion that isn't necessary for where we're going, as long as you can trust me. And I'm, to be honest, trusting others because I've been through various chapters of statistical mechanics textbooks multiple times, and it doesn't always click. So I'm going to kind of take this as, that it works. So the average energy of the sample is related to the partition function. So I've used this bar symbol to indicate average. If I multiply by kBT squared, and then I take the partial derivative of the partition function with respect to temperature, that's going to give me the average energy of the sample. So for example, if I wanted to do that for the rotational energy here, I can take the partial derivative of this quantity with respect to temperature. That's not very hard. This term is linear in temperature, so I can get that quantity and then multiply that by kBT squared, and that's going to give me the average rotational energy of my sample. And I can do that for all of these various quantities. I could do that for my translational, I could do that for my vibrational, and I could do that my electronic energy. That is the electronic energy, actually, that doesn't work in that particular circumstance. The electronic energy comes from the electronic structure, which is a topic for a different day. But for the translational, rotational, and vibrational, I could take those derivatives and estimate those average energies. So I don't remember why I wrote this. Oh, yes. For all intents and purposes, we're talking here about the average energy. The quantity of energy, I think, is a pretty confusing, like, what do I mean here? If I'm sitting in a physics class, I might think that this is the kinetic energy. From a chemical engineering perspective, it's not too straightforward because I don't really think about energy. I think about like enthalpy or internal energy. The energy here that I'm talking about is, for all intents and purposes, equal to the internal energy of the sample. So internal energy U. So that's a thermodynamic quantity that we're aware of. I can also use the partition function to get the entropy, and again, this equation comes from statistical mechanics, but if I take the Boltzmann constant and multiply that by the natural log of the partition function, that's going to give me the entropy. So for example, for an ideal gas, the translational entropy is going to be kBT times 2 pi m kBT over h squared to the 3/2 times v. That's going to give me the entropy, or the translational entropy of that sample. So that's the translational piece that if I wanted the entire entropy, so if I said like E total or equals U total equals E elec plus E ib plus E rot plus E trans, S total is going to be the same thing. S elec really doesn't exist. The electronic entropy doesn't really exist for these molecules. I should write here. We'll say exception is E elec. I'm just going to leave it at that. So we've approximated the partition function very significantly there by saying that it, for the purposes of the partition function, we're basically saying that there's only one contribution to it, and that is the ground state. That's totally fine and totally valid. But when we want to use this formula here to back out energy, we erased all the information that's there. So we can't use this formula, we'll say, since so we can't use this formula here, but that's okay. I can explain, if you're interested, how to account for that electronic energy piece. And actually, if we get to that later in the class, we will see that. All right, so that is basically how we use basically partition functions and how we use them to take energy levels into quantities that we are more familiar with.